welcome. Welcome back, everyone. Thanks to those of you who are here in person. It's always easier for me to not talk to a room of empty chairs, so I appreciate it. And also hello to everyone who is watching this remotely via Zoom or potentially asynchronously on YouTube. Yeah, welcome to ME309, which is structural mechanics. There we go. Structural mechanics is kind of this nice in-between course. If you like mechanics of materials, this is kind of the perfect next course for you to get to really dig into really the way the things around us behave when you push on them, pull on them, twist them, anything you can think of. And it kind of serves as a intermediary between mechanics of materials, which is a bit more of a, let's introduce you to the concept of stress, let's introduce you to some of the concepts of how things deform and how do we handle those deformations. And this is kind of in between class between that and what you would take perhaps in a master's or a graduate program on the theory of elasticity, which is very technical, very mathematically intense, and at times it can be very kind of abstract. And so this class, I hope, kind of sits somewhere in the middle where it's not quite as abstract as a linear elasticity class, but not quite as oversimplified and as basic as you'll find in a mechanics of materials class. So if you can, load up the syllabus. If you're here, hopefully you'll be able to see it in just a second. There we go. All right. So I sent this on the chat. I will also send this in an email later, so you'll all have a PDF copy of it. Let's see. So if you're here, you know you're in 203 photonics. Class is 9 to 10:45 on Tuesdays and Thursdays. I don't know why it says Tuesdays and Wednesdays. I'll fix that. Office hours are Tuesday afternoons from 2 to 4 and Wednesday mornings. It's listed as a discussion section. We usually have a GTF who maintains and runs kind of a problem-solving question on a homework problem or something. But we don't have one this year, so I'll do that as like an office hours. So basically, just log on to the office hour link, which is in the Learning from Anywhere part here. So there'll be office hours on Tuesdays and Wednesdays, Tuesday afternoons and Wednesday mornings. There's a textbook for this class. It's this one, Ugrall, Advanced Mechanics of Materials and Applied Elasticity. I'm generally pretty hesitant to ask students to buy textbooks. I appreciate how expensive they are. I would say this, if you imagine yourself doing something in an area of solid mechanics, structures, something related to this topic, this book is kind of indispensable to the point where you can get rid of your mechanics of materials book, but keep this one. Like, this book has all the mechanics of materials stuff and all the stuff we're going to talk about today and introductions to finite element stuff. So this book is kind of the best of all the worlds. So if you're going to have one book on solids or structures or mechanics of materials type stuff, have this one. It'll last you a good while, and it'll be a nice reference for you going forward. There's tons of stuff in here that we won't have time to cover in this class. Like, it's really rich. It's also got a ton of problems, examples. It's a really good book. It's Ugrall. If you find the 5th edition, that's fine. There's really not a ton of difference. There are some things better about the 6th edition, but it's not stuff that we'll cover in this class. It's stuff like more advanced things on plates and shells, stuff for more complex structures, a little bit more problems. So it's not just a cosmetic upgrade to 6th edition, but if you want to save some money, find the 5th edition. It's you'll be totally fine. I think all the homework I based is on the 5th edition because it was a couple of years ago. But I really think that book is worthwhile. All right, so if you're here, you're able to get on the Zoom ID. I will be posting videos of these classes to a YouTube channel. Usually I get them up either later the same day of the class or the next day, depending on when Zoom gets me the video back. So I try to post them to YouTube. There's a YouTube channel that I'm linking to in the syllabus here. And it has some videos from last year when I taught this class in the spring. So you can either ignore those or not, but they might just be, helpful. If you don't know what this class is, I tried to give a brief overview. It sits somewhere in between like a graduate level elasticity and an undergraduate level mechanics of materials. It is really trying to talk to you about solid mechanics, kind of elementary elasticity, and providing you a little bit of a bridge between the very oversimplified stuff you see in mechanics of materials and then the very overly complicated, because it needs to be, but overly complicated things you'll see if you were to say graduate and go start working doing finite element analysis. It's a pretty big leap to go from mechanics of materials to that. And this class is trying to kind of help bridge the gap to show you a little bit what's under the hood, a little bit of the equations that your finite element solver is actually trying to solve, which are different equations than the ones that we solved in mechanics of materials. And so this class is kind of trying to provide a little bit of a bridge between there. This is kind of a little bit of a work in progress. I've taught this course about 5 times, and I've for a long time been really unhappy with it. And so I'm trying to take advantage of the fact that we're in a new format and trying to rethink and revamp this class a bit. And so that means a couple things. One, it means I have some new ideas and some kind of new goals that I'm trying to accomplish with this class. One of those being providing you all with kind of conceptual tools to be able to estimate things. I feel like that's a really important skill for an engineer, to kind of be able to do the back of the envelope calculation, do the harder calculation, and then go to your finite element solver when you need it. Usually that's the process. And so I'm hoping that in revamping this course a little bit, I'll be able to kind of give you some of those conceptual understandings of how structures behave. It's something that's really emerged in the last, let's say, 15 to 20 years in the mechanics community, which is where I do my research in. I study the mechanics of slender structures. So that means I'm looking at how rods and springs bend, how plates deform, how shells behave, and how do we use these to create new and interesting structures. And over the last 20 years or so, there's been a lot of people who are trained in different fields using ideas from structural mechanics. And that has really kind of broadened the way that we talk about the field. And for a long time, it was kind of like, all right, let's dive into some partial differential equations, derive some stuff, and then you're left with a boatload of math and very little understanding of what you did. And I'm trying to kind of make this class a little bit more conceptually connected to some of the questions you might have about how a structure is going to behave. How do I estimate what's going to happen here? So that is the plan for how I'm viewing this class this semester. I will tell you, I will probably make some mistakes, switch some things around, and forget that you haven't seen X or Y first. So just tell me. I'll kind of rely on you to let me know if something's not making sense or if I'm assuming that you know something that you don't. So I'll need your help this semester more than usual because I'm trying to mix things up and change things around, and that means I'll probably overlook some stuff. And so I'm just kind of throwing this out there to all of you. Jump on chat, unmute yourself to ask a question, and if you're here, ask questions as well, because I'm hoping the end result of this will be a more enriching class, but it'll come with some mistakes that I make along the way. So the goals are listed here. Here's the course schedule. It's kind of a rough one, rough in terms of things might change around as I'm shuffling the order of things. You can kind of see it here, right? Like in the reading listed on the syllabus, it starts out in chapter 10 and then goes back to chapter 1. That seems kind of weird. But there's a method to that madness. I kind of like the way the class starts now. It helps provide a bit more of a conceptual understanding by using ideas from energy and how we understand principal minimum energies and energy tending towards being a minimum. Using that concept, you can actually do quite a bit. At the moment, I'm looking at 2 exams, a midterm and a final. There's a chance if I can figure out how to come up with a good project plan, we could switch out that final exam, which to be a project that involves a little bit of math, a little bit of finite element work to kind of tie things together. I'm hoping to get to that point because I think that's a more useful use of your time than an exam. At the moment, we'll kind of live with this plan of having these 2 take-home exams and some homework assignments throughout. But I'm really trying to see if I can come up with a couple of good projects that could possibly take the place of those. Because I think at this level, as most of you are all seniors, I think you'll get a lot more out of doing some math, tinkering with console, kind of trying to figure out some problem that you're interested in. I just need to come up with some project outlines that are kind of the right difficult level. All right, let's scroll down here. Let's see. There's a ton of information in academic conduct, student performance. I kind of, I feel like early on in your college career, there's a lot of emphasis on kind of just grinding to get the best grades you can possibly get. And I think it's somewhere in the beginnings to the ends of your senior year, towards into your graduate career, there's a little bit of a mindset shift in which you kind of realize, like, oh man, I gotta know some of this stuff. I wish I wanna learn this material. And that knowledge ends up becoming a little bit more important than the grade attached with it. And I have on here, work together. If you want to work on a homework assignment together, work together. Just let me know that you're working together. I want you to leave this class with an understanding of structural mechanics. That's my goal. I'm someone who's going to be less kind of a stickler for grades and more of a professor who's going to be interested in seeing you demonstrate kind of mastery of a topic, or seeing you be aware that you don't yet have mastery of this topic and you'd like to get there, and you're going to work with me or work with your peers or to understand what you don't understand yet. And so I'm still trying to find the best ways to kind of find a balance between understanding that we grade your performance, but in my mind, I really want to see mastery as the goal. I want you to master this topic because that's what's going to be expected of you. If you're going to leave here, you're either going to go to graduate school or you're going to get a job, and they're going to say, oh, you took structural mechanics, you know how to do this, and I want you to know how to do whatever that thing is. So obviously we're in a brave new world here. I assume now that we're in our 3rd semester of COVID-related things that most of what I say in bullet point 3 here is probably very well known to you at this point. I don't imagine there's going to be much of an issue there. I am adding kind of, I think the pandemic has emphasized the importance of issues of not only physical health, but mental health, issues of tied to access and inclusion. And so I add some of these discussion points on my syllabus because I want to be there if you need help kind of resolving any of these issues, whether it is struggling conceptually with some of the topics we're covering, or struggling because of any variety of aspects that could lead to challenges within mental health, anxiety, stress, accessibility. Any of these aspects can affect your performance. I'm acutely aware of that. And so I kind of add this on here as a way to potentially start a dialogue. And so if there's anything I can do to help, please reach out to me, whether it is specifically related to this class or things that might be tangentially related to your performance. And I'll do the best I can to help you with those things. And so I listed some details and some places you can go for resources on here, but in the end, I just want you to know you can come to me if there's anything I can do to help. I will do that. All right, before I move on, questions about the syllabus. I'll fix the date here. I don't know why it says Tuesday and Wednesday up there. Any questions about the syllabus? Check to see what the chat is doing. No? Yeah.
Is the discussion section that we have on student link, is that just the office hours?
Yeah, usually we have a graduate teaching fellow who runs a discussion section that is really just more of a let's do some book problems kind of a thing. I don't know why we don't have a TF this year. I'm not sure. I'm going to look into it. But in the meantime, until I sort that out, I'll just handle it as an office hour. So basically log on to Zoom and I'll kind of treat it as an office hours. If you want to work on specific things or if there are general questions you have, we can do that there. It's kind of a holdover, this discussion section, from a while back. I typically treat it as an office hours. I think it's been something that is very poorly attended over the years. Not the office hours part, the discussion section. And so, yeah, I'm basically right now, until I can find out if we're actually got misassigned and we have a TF joining, then I'm going to treat it as just an additional office hour. So you don't have to go. You can go if you have questions. Other questions? I'm pretty terrible at Blackboard. I'm trying to make Blackboard, I'm trying to get better at it, but I do post a lot of resources on my website as well. And so if you go up to, oh, come on. Well, it used to show what it was up there. This is bu.edu. I'll type it in the chat. bu.edu/MOS, Mechanics of Slender Structures, /courses. I'll put this link on my syllabus as well before I email it out to everybody. I will try to post things on here, including, like, for instance, the syllabus, videos from our class. You can kind of get a sense here. This is from the fall. So this is a different class, but I posted kind of videos and a PDF of the notes I'll be writing on my iPad here. And I'll post the PDF of these notes on this website, along with a link to the YouTube channel and then some various code that we'll end up using throughout the semester. So we typically do some stuff in Mathematica. If you've never used it before, I'll try to give you a little primer on that. And the other thing I'm trying to do this semester, which could work and be awesome, or it could be a disaster, we'll find out, is I'm trying to incorporate more work with Console into the class. You can, I believe all of you can access Console through Citrix. That's here. We're in a class, so we have a class license, and I believe the primary one for us would be this structural mechanics module. They're all available, so you can use all of them. So if you just Google Citrix and Console for BU, it'll tell you how you can access it. I wouldn't worry about it right away, but this is something I'm trying to build in to give you a little bit of experience analyzing stress within structures using a finite element solver. I feel like many of you have encountered Console and, say, fluid mechanics. So if you've never encountered it before, you'll be just like a hair behind me who's pretty terrible at it, but is learning. So we'll see what we can do to make it a useful tool to help our learning here. All right. What questions do you have for me? I've been talking nonstop.
So
yeah,
I know you were talking about like maybe changing the final for a project,
Mhm.
but like it also in the course description includes a design project already. So would that be 2 projects? Or?
No, it would just be one. Yeah, I've in the past, it was always a project, but then I had a lot of seniors asking if we could not have a project coinciding with senior design at the same time, and so I kind of switched it to an exam, and I'm hoping now to have some sort of a project that is more computational, not a massive like build something kind of thing, but like something that would be like doing a calculation, doing some finite element analysis, doing a comparison. It wouldn't be 2, but it would be, the goal would be to try to make a project that doesn't kind of burden you all and make your April, early May awful. But I feel like a project in which you actually dive in to something like Console and do some finite element modeling would pay off for you longer in the future than another exam. So it's kind of a me trying to find that balance for you all. If we didn't have senior design, it would definitely be a project. So, yeah. But I will. I'm trying to find a good balance there. Any questions? I hope all the people online can hear me and are having no trouble with seeing what I'm presenting. So with that, I might just get started. Any, yeah, maybe? All right, cool. How similar are the exams to the homeworks? That's a good question. I would say pretty similar, although the homeworks tend to be very technical. It's like, okay, here's a structure, here's the loading, calculate the stress in this direction or the deformation here. And I sometimes try to add, well, not sometimes, I usually try to add some conceptual questions to the exam to try to get at, like, what do we mean by this concept? What happens if we were to change this to that? How would that qualitatively change it? So the homeworks are typically entirely quantitative. calculate a stress, calculate a deformation. The exams, I do a mix of that with some conceptual questions. So fairly similar, but I like to be able to ask about conceptual ideas on these exams, because I feel like that is, in a lot of ways, more important than the kind of technical calculations. So that's a good question. All right. So I feel like I've given you already a little bit of a, what is structural mechanics? It sits somewhere between mechanics of materials and linear theory of elasticity. It typically, what we're thinking of when we think of structures are three ideas. We're typically thinking about trying to analyze their strength, and now strength is typically a material concept. It's kind of saying, if I apply this much load to this object, we know from mechanics of materials it's going to lead to the structure itself building up stress within there. And then we also know that there's some ultimate stress in which this structure will start to fail. Maybe it'll yield, maybe it'll fracture, but there's usually some sort of material limit to the amount of force you can apply to an object. And so this is typically characterized by how well does that material resist permanent deformation. And you usually see permanent deformation, something like plastic yielding, or brittle fracture, etc. And like I said, these are typically something that emerges from the material properties. The material, we would say it behaves linearly if under that loading, it doesn't exhibit any permanent deformation. Or it doesn't, there are more complicated ways to make that distinction. But for right now, if you think of it like a spring, if I pull on it and I let it go and it goes back to its original state, it deformed, we'll say it deformed linearly in that process. That distinction is kind of important because the other two things that we think of when we think of structures are stiffness and this is really a measure of how does the structure resist deformation, or in some cases deflection. Kind of the same word, but usually used in slightly different contexts. And you can see that in the stiffness case, really we're talking about shape changes, deformations. And so the stiffness of a structure is typically related to the geometry. And in that case, the linear behavior of the geometry. So typically it's, again, go back to the spring. You're pulling on the spring, it's deforming, it's changing shape a little bit, but you pull on it a little bit, it elongates a little bit, you pull more, it elongates more. So there's a linear relationship between how hard you pull and how hard it changes shape. So this is typically stiffness is typically related to the linear behavior of the geometry. I make this distinction about stiffness being related to kind of the linear deformation of an object, because stability is the third S, third key concept for how structures deform. And stability is the ability of a structure to maintain an equilibrium configuration. The classic example of, I feel like when you see that definition, I feel like at first your thought is kind of like, it's an equilibrium configuration. Why wouldn't it maintain that? And I'll just kind of remind you of what happens if you take a pendulum and you have this pendulum that's kind of spinning back and forth. If you spin that pendulum fast enough and you get it up vertically, you do a force balance on this vertical pendulum, it's in equilibrium. It's totally happy up here. But you know from experience that if you the wind blows the wrong way or you vibrate a little bit, this thing is going to immediately fall back to its downward configuration. So equilibrium states can be stable or unstable. And so oftentimes the stability of a structure is really one of the most important characteristics of it that we're looking to quantify, because there's this kind of contradiction in structural mechanics, which is that typically the thinner and the thinner you can make a structure, the stiffer it's going to behave for requiring less and less material. Think of something like a soda can. Soda can is remarkably thin cylinder. You know from experience that they're actually pretty stiff. Like you can kind of take one and push on it pretty hard, but then you push just a little bit harder and it collapses completely. And that distinction is not unique to soda cans. Oftentimes, when you optimize a structure, so by making it thinner so that it can be really lightweight, so that it can be really stiff, you're also at the same time kind of making it less stable. And so it's this trade-off that you're looking for. You're kind of trying to figure out like how thin and light can I make this thing? I don't want shipping costs. I want my airplane to be as light as possible. I want to burn as little as fuel as possible. Again, a cylinder with a spherical cap for a nose and a spherical cap for the tail and beams or plates for wings. I want those things to be as thin as possible, but you know, or what I'm hoping you'll know by the end of this class, is that what a structural engineer is trying to balance is I can make them thinner and lighter, but I'm also making them more sensitive to instability. And the reason, and you can kind of, this to me I think makes it obvious that the geometry in a case of a stability problem is nonlinear. Okay, think about the soda can example. You take your soda can, you kind of push on it a little bit, it's going to change shape a tiny amount. You push on it a lot, and the geometry fundamentally changes when you crumple a soda can. It doesn't look at all like a cylinder. It's got wrinkles and creases as this thing's been crushed. So typically there's this distinction between kind of linear effects and nonlinear effects. In general, the linear effects are simple to handle, and the nonlinear effects are more interesting and kind of compelling, because it's really striking when you see a soda can get crushed for just putting a little bit more force on there. These are typically the three things that we're trying to analyze when it comes to a structure. How much stress is in that structure? Where is stress concentrating? And how does that stress compare to the material failure point? How much deformation can we allow for this structure? How comfortable are we with the amount that the wing of your airplane can go up or down depending on loading? How much deformation do we want to allow? And then how confident are we that our structure is going to remain stable through the typical loadings that it's going to experience? These are kind of the three aspects that we're trying to get at in structural mechanics. So oftentimes, what you'll see us doing in this class are solving for stress in a structure, solving for the deflection or deformation of a structure, and doing some sort of stability analysis to see if a structure is going to pick one equilibrium configuration or pick a different one. So these are kind of the three pillars of structural mechanics. Do these make sense? Am I missing anything? There's typically two ways that we can evaluate these properties of structures. They're equivalent, and depending on the situation, depending on the problem, it might be advantageous to use one approach over another approach. These two approaches one of them is pretty familiar. It's the stuff that you've had kind of beaten over the head for the last 2.5 years of your undergraduate career, which is a method of equilibrium. Sum of the forces equals 0, or sum of the forces equals mass times acceleration. And we can use that, draw a free body diagram, calculate what the force is or what the stress is. And this is referred to generally as the method of equilibrium. We typically have there's technically 4 sets of equations, but we generally ignore the 4th one until you're kind of really at an advanced graduate level. And so the 3 others are equilibrium, equations. So that is what I was just saying. Those are your sum of your forces equals 0. There are, in addition to equilibrium equations, what you were introduced to in mechanics of materials were kinematic equations, and the idea that if you consider the deformation of an object, that allows you to solve tricky problems, like for instance, problems that involve statically indeterminate structures. So you have a bar stuck between 2 walls and you're heating it up. That's a problem where if you just look at the equilibrium equations, you end up with more equations than you end up with more unknowns than you have equations to solve for them. And so then you say, what do I do? Oh, you turn to the kinematic equations. The kinematic equations are basically a way of saying, what do I know about deformations? So in that example of the bar stuck between 2 walls, you know that the bar can't get any longer in the x direction because there's a wall there. And so you can put constraints on deformation, and that's where you can get your additional equation to solve for your unknowns. So these would be kinematics. This basically means, in statics, structures don't deform. In mechanics of materials, they do, and that enables you to solve harder problems. And the third is constitutive equations. Constitutive equations are just how do you relate the stresses in the object to its deformations. The simplest constitutive equation that you're all familiar with is Hooke's law, which says that I can take stress and relate it to strain through a linear proportional constant known as Young's modulus. Stress has to do with your forces. strain has to do with your deformations, and there's a proportionality between forces and deformations. The simplest possible constitutive equation is a linear one, and that's the one you probably are a bit familiar with, is using Hooke's law. So this is the typical method of equilibrium. This is where your book starts. And this is where I typically started this class for many years. I am switching it up this year because I am hopeful that using the second approach can be a bit more instructive and kind of conceptually make a bit more sense than the method of equilibrium. The challenge with method of equilibrium that we're going to see probably in a few weeks, is that what you realize is that we made a lot of assumptions in mechanics of materials. And what those assumptions did is they allowed us to work with algebraic equations. Stress equals modulus times strain. The stress in a bent beam equals the moment you're applying to it times I over the second moment of area. All these things they're a pain to use sometimes, but they're just algebraic equations. In reality, the equations of equilibrium, the equations of kinematics, and the equations, let's say the first two, the two of these three here, in reality, are partial differential equations. They're generally sets of partial differential equations, and they're really difficult to use. For one reason is that, for the most part, I don't know if you know that much about partial differential equations, but ordinary differential equations are not that bad. Ordinary differential equations are guaranteed to have a solution. That's a win, right? And they're also guaranteed to have a unique solution, which is also good. They taught, if you're really into math, you would have taken a class on differential equations, and they would talk about those two ideas as being existence and uniqueness of solutions. The challenge with partial differential equations, which in reality, as you'll see, these are governed by partial differential equations, and these are partial differential equations as well. The challenge with partial differential equations is you're not guaranteed that a solution exists. And if a solution does exist, you're not guaranteed that it's unique. And so solving partial differential equations is a real challenge. There's only certain instances in which you can do it analytically. And that's why the finite element method is a really predominant computational tool for us in solid and structural mechanics, because these are equations that we need to solve iteratively, piece by piece, kind of going from where we had a solution to where we, as close to that solution as we could possibly go, and then moving forward and solving it one step at a time. I think it's vital for you to learn all these things, and we will a little bit through the semester. But I want to introduce you to something that's probably a little less familiar. And this is a second approach. Which are all based on energy methods. I was not trained as an engineer. I was trained as a scientist, and trained as a scientist, you're very comfortable thinking about the concept of minimum potential energy. We always think about energies. We think about free energy. We think about the energy in a gravitational potential, energy of a molecular bond forming or breaking. And what's nice is that these methods are equivalent. They're really connected. And you're going to see that. We can use the energy methods to derive the equations of equilibrium. They're very equivalent methods, but they each have their own advantages and disadvantages. And for the energy methods, it becomes, in my opinion, easier to start to estimate what's going to happen, to start to approximate a solution. If you can't solve it exactly without going to a finite element solver, maybe we could approximate it and see, is this a reasonable structure that we're designing here? And I really like these methods because I find them to be fairly intuitive. Now, that intuition doesn't come immediately, so it'll take some time to get used to it. But I do believe that using methods from kind of calculating the energy of a structure and calculating the work trying to be done on that structure, you can start to learn a lot about how that structure is going to behave. And so this will require us to introduce the concept of strain energy, which is in your Mechanics of Materials textbook, but I would bet a lot of money that your semester ended before you got to that chapter. And so I think we're going to start there with this class and see if we can use that as a tool to at least get some conceptual understanding of how structures behave. And so this is kind of the outline for the whole class. Or at the very least, these are the topics that are kind of at the heart of structural mechanics. Is we need to know about the strength, stiffness, and stability of our structure. And there are two ways to do it. We can either use methods of equilibrium or these energy methods. And they're complementary. They are equivalent. They just require kind of different tools, and we'll kind of be bouncing back and forth between them a bit through this semester. And so this, in a sense, is really like the kind of overview for the goal of this semester, of this term. And I kind of want to, I think another thing that gets lost when teaching structural mechanics is we spend a lot of time talking about beams. And I think there's a little bit of like, why are we always talking about beams? And I want to kind of point that out at the beginning to answer that by saying structures are generally kind of assemblies of, let's say, 3 types of components. You're typically a structure, so like look around wherever you are right now. You know, we have a railing in here that's like a beam resting on 2 beams mounted to the floor, which either this floor is a 3D body and is, you know, really thick, or maybe it's a plate. We have this table here, which is a plate sitting on some beams that are also sitting on some beams. We have a chair, which is, what do we got here? This is curved, so we'll say this is a shell, sitting with a plate and a couple of beams over here. And underneath we have 5 different beams sitting there. If you remove these panels on the ceiling, sorry people at home, you can't see that, but just imagine a tacky office building ceiling. And you'll see that there are beams running across and these little plates in between these panels here. Those beams are actually connected. The bigger beams are going to be connected to I-beams that are going to bear the load of these walls, which these walls, if you were to kind of just knock a hole here, you would find that they're going to basically have studs of some sort running vertically from top to bottom. It's going to be carrying the load from whatever's above us to the ground. So you kind of have like beams or columns. Columns are just beams that are vertical. I don't know why we use different words, but we do. So there's going to be basically columns bearing the load for all these walls here. Plate. You start to look around and say, like, how do I simplify this stuff? So you can either take the approach that all these things are really intricate and unique, and I have to really model this thing perfectly to see how it's going to behave, or you can kind of take the oversimplified view that I take, which is like, wow, most of this stuff are beams, plates, or shells, and to some degree, 3D solid objects. You know, the ground is a three-dimensional solid body. But a lot of the structures you're used to seeing and trying to model really are assemblies of beams, plates, and shells. And we, in this class, spent a lot of time working on beams for two reasons. One, actually, most of the things you're looking at are beams, or at least the things that are bearing load. You know, as I mentioned, the columns that are running vertically here for your load-bearing wall, most of the work is being done by these beam-like structures. The same thing with our railings here. The same thing with our table here, which is taking the load that I'm pushing onto the ground. Beams are doing a lot of the work. So it's really important for us to know what are the stresses, what are the deformations, how these beams behave. That's the first reason why we spend a lot of time on beams. The second reason is shells are really hard. The equations for shells are, they're about as complex as the equations that describe general relativity. They take very much the same form. I would argue that they're slightly harder for some esoteric reasons that we can talk about offline, but they're remarkably hard because for a couple of reasons. One, and probably the easiest one for you to imagine is think about how much time you spend in your undergraduate career thinking about Cartesian coordinates, you know, X, Y, and Z. Well, shells are curved. It doesn't really do much good to use Cartesian coordinates to handle this shape right here. This shape right here on the back of this chair is kind of more similar to the shape of a Pringle potato chip. It's kind of curved one way here, and it's curved another way here. The coordinate system that you live on here, Cartesian is useless. So you need to use nonlinear geometry just to write down the equations. And then you have partial differential equations with coordinate systems that are immensely complicated. Shells are hard. Plates are just flat shells. Plates are a little bit easier because you can start to use Cartesian coordinates again. So there will be some stuff in your book, and I hope some stuff that we'll be able to talk a little bit about for plates here. But plates and shells are really, really hard, and it takes a lot of advanced kind of mathematics to be able to work with them. But the other reason is if you understand how beams behave, you can kind of intuit a little bit of how plates are going to behave and shells are going to behave. You can start to say, well, maybe my shell is just a connection of a bunch of different curved beams. If I know a little bit about how beams behave, maybe I can approximate how this is going to behave. And so these are the reasons why we are going to spend a lot of time talking about something that feels a little bit removed from, you know, the complex structures all around us. But if you really think about these structures and you start to oversimplify and say, okay, well, can I strip this thing down to the simplest types of forms? If you understand how beams behave, you can do quite a lot, both in terms of checking your intuition, but then also when you're doing something computationally, going back and saying, does this make sense for how I would imagine it if this was simplified to something like a beam or a curved arch? Oops. Sorry, everyone. So that's the overview, and this is our first day back. Was my first day back. I think some of you all had class yesterday. So I've been chatting at you for like an hour. So why don't we take like a 5-minute break? If you have any questions, either yell them out on Zoom or type them into the chat box, and then we'll get back to this around 10 o'clock. All right? All right. So, for reasons that no one quite truly understands, everything in the universe tends to minimize its action. What is its action? Its action is the integral of the energy over time. The way we think about this in structural mechanics is we often ignore one half of the energy. But we know that there's two types of kind of energy that we're used to thinking of: kinetic energy and potential energy. And for structures that are not vibrating or oscillating or experiencing any inertial loads, you can learn a lot just by evaluating their potential energy. And the reason is that big statement of everything in the universe tending to minimize its action, which we'll talk about. We're going to spend some time talking about that in several lectures from now. In the absence of kinetic energy, if you can ignore some kinetic energy, that statement reduces to one that's a lot simpler to handle, which is if you want to know the shape of an object that's being deformed by some loads, the shape of that object will be determined by whatever shape minimizes the total potential energy of the system. So the shape of a deformed object let me just write it a different way is so the nice thing is if we can write down total potential energy, energy is a number, right? It's a scalar. And so you can imagine kind of assigning, so like I've got my, what do I have here? I've got my sheet of paper and I'm doing some crazy thing to it, bending it, twisting it, all sorts. I could imagine under these loads an infinite number of different shapes that this thing could take under these loads. The one that it will actually take, the one that you're seeing, the one that you actually can realize, is the shape that minimizes the total potential energy. So what that means is if you could somehow create a computer program that you feed in the loads and it could go through every single possible shape that this thing could take, every shape under those loads. It could calculate the total potential energy, which is just a number. It's a scalar quantity, it's a number. And then it'll just pick the one that has the lowest number. That'll be the shape that you see, is the one that minimizes the total potential energy. And so if we want to use these energy methods, we have to know a little bit about what the total potential energy of your system is. Now, there are two approaches that are important for you to know. I'm going to write them down so you're aware of them, but they're not going to really affect what we're doing this class. And you'll see why in just a second. There's two kind of different ways to handle energy methods. One is known as Lagrangian Mechanics, which is probably what you encountered if you took a class on dynamics. They probably, I don't know if they use this term Lagrangian mechanics. You might have encountered the Euler-Lagrange equations. These are a way of formulating energy where you say, I'm going to calculate the difference between kinetic and potential energy. So I'm going to say I'm going to have a Lagrangian L, which is equal to just the difference between kinetic and potential energy. An alternative, but entirely equivalent way of handling energy of a system are what's known as Hamiltonian Mechanics, in which they say, all right, I'm going to look at, the total energy in my system as being the sum of all the energy. So it's going to be the sum of my kinetic and potential energy. These seem remarkably similar. They lead to different sets of equations that you solve. They give you the same answer. In general, one of them has more equations to solve, and the other has fewer equations that are a little bit harder to solve. And so you have a trade-off of like computational cost. Like, do I want to solve more equations that are simple or fewer equations that are harder? And honestly, depending on the problem, one of these methods is generally preferable. And you have to kind of be experienced to play with it. For our sake, we don't really have to care about either of these things. And the reason is V is what I'm writing as our potential energy. Let me write that down here. This is potential energy, and T is kinetic. For the sake of this course, a kind of introduction to solid mechanics or structural mechanics, we don't really have to care about any of these subtleties because we're really going to look at static problems in which all we're going to concern ourselves with is the potential energy, V. We don't need to really think about what we're adding to it because we're adding 0 to it or we're subtracting 0 from it. So we can focus on just the potential energy. And it goes back to this statement of the shape of the object is going to be the one that minimizes the total potential energy. So what's the total potential energy? So the total potential energy for an elastic object is composed of the internal strain energy, which we usually write with the letter U, and to that internal strain energy, we're going to add to that any potential or potentials from external loads. The strain energy is like the energy in a spring. It's like if I push on a spring, how much energy am I storing in that spring? And that if I let go, that energy is going to be released. And the external potentials are going to be, what work am I trying to do on this thing? I'm pushing with some force and causing some displacement. That's going to give me a potential to do that work that you're trying to do. So if I want to calculate the strain energy of an object, a three-dimensional blob of something like Jello, what I do is I take the stress in that material and I multiply it by the strain energy, and I integrate that quantity over the volume. Why do I do that? Well, this is strain energy, so the stress has to be coming from deformation in this object. So there's this coupling of stress and deformation. But also, if you just quickly do dimensional analysis on this, I can say, well, okay, the units, which I'm going to denote by my little brackets here, the units of stress are what? Who remembers? Pascals is right, and pascals are Newton per meter squared. So if you think about like pushing on a bar, you have a force that you're applying, and you have to divide that force by the cross-sectional area that it's being exerted over. And so you end up with a force per meter squared, which is a Pascal. So we'll write this down as Newton per meter squared, which is also equivalent to a Pascal. Strain is dimensionless, it has no units. If I integrate over dV, what are the units of that operation? The triple integral, integrating over dx, dy, dz if we're in Cartesian coordinates. And so I would expect to get what out of that? Meters cubed. Yeah, you're going to get a volume. Exactly. So that means this entire quantity, the integral of stress times strain over the volume, is going to yield something like the integral of stress times strain dV. And if I just want to evaluate the units of that quantity, what I see is I get newtons per meter squared times meter cubed, which is a Newton meter. Newton meter is an energy. So this quantity that I've denoted up here, the integral of stress times strain over the volume of my object, is an energy And it's what's referred to as the strain energy in my material. Now this, again, I'm gonna show you this, but I want you to kind of ignore it just for a second. But I want to show it to you for completeness, which is that this gets actually a little bit more complicated because, as we know, stress and strain aren't scalars. They're not even vectors. They're actually tensors. And so we have to be a little bit careful. So you might not see it written like this. You might see it written like this, where we say, I'm going to integrate over the volume of sigma ij. You might remember sigma ij from mechanics of materials, which is the fact that it is a tensor that has sigma xx, sigma yy, sigma zz, and then off diagonal components like sigma xy, sigma xz, and then those are all symmetric, so you fill in the rest of it accordingly. It's a tensor. Tensors typically are very terrifying to undergraduate students, graduate students, and many academics of all ilks. They're very unintuitive objects, but they are physical quantities nonetheless. Just like a vector is telling you what magnitude and direction something like a force or velocity is going, a tensor is really just telling you at any point in the material there are stresses in multiple directions acting on that material. And stress is point-wise. If you've ever done something in like SolidWorks or Creo, where you ran like the finite element, what happens if I push on this thing? You see like this beautiful color-coded structure that's kind of rainbow colored from blue to red. What it's doing is it's coloring each pixel by a stress value. It's saying, oh, the stress at this point is this color. So what you're really handling here is two tensors multiplying each other. Don't worry about the notation for right now. Don't worry about the subscripts. I'm writing this down just so that way if you ever see it, we'll go into these details. But for right now, I want you to know that it's not quite as simple as we're taking this two scalars and integrating over their volume. We're actually doing something with two tensors, and that can cause headaches. It can get even worse because the way I've written this down right here on the board, that's when everything is in Cartesian coordinates, everything's flat, everything's small deformations. And I mentioned if you're doing something with shells or you're doing something with nonlinear geometry, nonlinear deformations, that things get more complicated. I'm going to write this down just so you can see it, but the math itself changes, and what you end up having to work with are quantities where we describe tensors with indices that are upstairs versus indices that are downstairs, and those having different physical meanings to them. We probably won't get into handling stuff like this, but if you ever see it, this is just the most general form to write down the strain. It's allowing you to handle things that deform in crazy ways that might be shells. It might be saying like, if I want to model what happens when I accidentally turn my contact lens inside out. That's this. Contact lens is a spherical shell. It's going to have curvilinear coordinates on there. It's going to have a large deformation when you turn your contact lens inside out. You really change that shape dramatically. And so there are general ways that we handle this. But for right now, I'm showing you just that for curiosity's sake. We're going to see that we can do quite a lot with just this simple conceptual understanding of strain energy being the stress times the strain integrated over the volume. So we've got half of it done, right? We've now got U. And now we got to handle what the potentials from our external loads are. These can take on a variety of forms. Again, the notation here is not important. I'm going to write down some notation. It will probably be messy to some degree, but for right now, I don't want us to focus too much on on the notation, what I want you to know is a couple of things. One, actually, hold on, let me write strain energy up here. So this is our strain energy. And we'll go over here and denote the potential. Assuming the external forces don't change as the object is deformed. This is a big assumption, but it's one that most people use because the problem becomes immensely more complicated if the forces do change with deformation. Then, if these forces don't change during deformation, then what we can say is that the potential of the external loads is equal to the negative of the work. I'm guaranteed to mess up the signs on this at some point during the semester. I'm terrible with signs and factors of 2. It's just one of the things that you'll come to learn about me, but I'll do my best to not confuse you too much. The potential of the external loads is the negative of the work being done by an external force. We know work is, say, force times distance. And so we can look at an increment of work. You probably learned about the concept of virtual work, maybe in statics, I think. We'll dive into virtual work again, so there'll be a hearty refresher on there. But for right now, I'm just going to kind of look at it this in an infinitesimal way and say that the kind of infinitesimal increase in work, the small change in work, delta dW, is going to be equal to my force that I'm applying. Depending on which notation you use, you might denote this as a vector with an arrow, which is dotted into some distance. We're in an infinitesimal amount of work, so the force would be dotted into an infinitesimal displacement. We're going to call our displacements U. We'll talk about this notation a little bit further. If you're going to use the same notation as I used before, in which we have I's and J's everywhere, these indexes, these indicial notation, which is my personal preference, then this would be written a different way. It would be written like this. Fi, oops, Ui, but that doesn't matter. For right now, we'll just say, well, if that's our infinitesimal change in work, to get the actual work, you got to integrate over that quantity. So we're going to integrate from, say, the B of dW to find that our work is basically equal to the integral of my force times my displacement and now forces can take on all sorts of different types. So this is a kind of in general true here. This is in general how we would handle work. But sometimes you have what are forces distributed over a volume. What does that mean? If I like have a here, why is this thing deforming? Gravity is acting on it, right? Gravity is acting on it. Gravity is a force that's acting on the entire volume of this object here. So this would be an example of what's sometimes called a body force or a force acting on a volume. The other common one that you'll see is magnetic forces. Bring a magnet here or something, it's going to act on the magnetic potential is going to act on the entire object. And so you might have, for instance, forces distributed over volume. And it'll look exactly like what I just wrote. It'll look like W equals the integral of the volume of my force vector and my displacement vector, dV. I'm changing notation here. Doesn't matter. I'm not even interested in you focusing on notation for right now. I want you to know conceptually that a force could act on a volume. Or this book that is sitting on this table is exerting a force on the table, and it's exerting a force over some surface area. So there's some area of the book here. This force has some weight. That weight is pushing on the table. And so this would be on if you're modeling the table, that would be a force acting over some surface. Not the entire surface, but some portion of the surface. So you might write that you have sometimes forces distributed over the surface, which would be, these are sometimes, this is going to be integrated over the surface instead of integrated over the volume. These are sometimes denoted with a capital T and called a traction force. But that doesn't really matter for right now. And this is usually integrated over some surface S. If there's a variety of concentrated forces, like I'm pushing on here with like 4 fingers, then the work can be written down as, instead of an integral quantity, if I have concentrated forces, then you might say that the work is going to be equal to the sum from I is equal to 1 to N of all those different forces acting on all my different displacements. The mathematical form of these is not really important right now. The conceptual idea is, I have strain energy, which is the integral of stress times strain over the volume. And I'm going to add to that potentials from external loads. Now those external loads they do work. The work is equal to the negative of the potential, and the potential is equal to the negative work. And the way those forces can do work depend on the nature of the force. If it's a force per unit volume, then you're going to integrate over the volume that the force is acting on, which is the magnitude of the force times the displacement. They can be forces per area. They can be concentrated forces at different points. And so our job, or my goal for the next class, is to start to give you some really simple examples of how we can calculate strain energy and how we can calculate a couple of different potentials from external loads, and how we can get a very conceptual understanding of what it means to kind of balance these energies and minimize these energies to find deformations. So what we'll do going forward is dig into this equation here a bit more. It turns out we can kind of split up the strain energy in our object. Think about mechanics of materials. We always said you have energy that goes into kind of stretching or compressing an object. You have energy that goes into bending an object, twisting an object, and then everyone's favorite, transverse shear stress in a thick beam. What we can do, what we will do next, is start to split up this term here into those different things I just said. So we'll take this total strain energy and say, well, the total strain energy is going to be the strain energy of stretching, bending, torsion, and so on. And it turns out that by doing that, we can really quickly learn a lot about how structures behave without doing anything complicated mathematically, just really basic stuff. It's just the idea that if we understand what strain energy is and we start to break down the strain energy into smaller parts, we can then kind of make get a conceptual understanding of how structures behave in different environments. I think this is a good place to stop. And it's our first day, so I don't want to bore you all to sleep. But are there any questions before I do pause for today? How about over here?
I just want to confirm, you said the 5th edition for the book is okay, right?
Yeah. Yep, you won't, yeah. And it's also fine if there's digital, if you find like a digital copy, it's cheaper too. I just think like if you're gonna spend money on any structural mechanics book or solid mechanics book or any kind of book vaguely related to the topic, this one is worth it. And I would get rid of your mechanics book, in my opinion. So, oh yeah. So I would ask to share the syllabus in the chat again. And just so you all know, I'm going to email this out to everyone. So I'm going to probably tweak it, my typo, but I will definitely email this to everyone as well, so you have a copy of it. And I'll post it to my website. Here's the link. I'll email it to everyone. I'll post it on my website. Yeah. All right. Thanks, everyone.